Welcome to the video lesson for the periodic table. We're going to talk about the organization of the periodic table today and the groups. Remember to take very good notes because there will be a Canvas quiz which you get to use your notes on. So the better notes you take, the better you'll do on the quiz. Okay, so let's get started. So the history, first of all, about 70 elements were known by about 1850. At that time, they did not know about the noble gases. And there didn't appear to be a good way of arranging or relating them. Matter of fact, some people called different elements different names, and so it was kind of confusing for the people who were studying that at the time. So a first guy to come along was the name of Mendeleev, depending on who's saying it. And he was the first one to place all the information known about the elements known at the time on cards. He arranged them by their atomic mass, density, different properties. So then he decided he was going to arrange these elements in order of increasing masses. And he noticed that certain similarities in their properties started appearing at regular intervals. Such that this repeating pattern is often called periodic. And so he was very instrumental in setting up the very first periodic table. And so in your notes, it's got a typo. It says 1896 for the date. So I need you to cross that out and change it to 1869. And his first table was published in 1869. And the cool thing is that he left blanks in the periodic table for undiscovered elements. And he predicted their properties. And it was really cool because when those later elements were discovered, they actually had the properties that he predicted based on the pattern that he had first noticed. Okay? There were some problems with his table, and that was a few elements didn't quite fit in the way that he was arranging it. And so the atomic mass arrangement didn't match some of the properties. And so, of course, that led to further work. However, of course, Mendeleev never received any recognition of his work, but of course we talk about him now, but the importance of the periodic table was not realized in his lifetime, which is kind of sad. So then along came the guy named Moseley, and along with Rutherford, in about 1911, discovered a new pattern. The positive charge of the nucleus increased by 1 unit from one element to the next when the elements are arranged as they are now in the periodic table. And the way that they are arranged now, of course, is by their atomic number. So this led to the definition of atomic number of protons, and the recognition of the periodic table based on atomic number, not mass. So the original periodic table was based on increasing atomic masses, and the current one that we use is based on increasing atomic number. So this brought up something called the periodic law, which is basically the name of this chapter and what we'll be studying, and that is the physical and chemical properties of the elements are periodic functions of their atomic numbers. So these patterns appear at regular intervals based on their atomic numbers. Okay, Moseley actually died at a very young age. This is just extra information. He was a victim of World War I. So the modern periodic table and the way that it's arranged, okay? Of course, we said it's an order of atomic numbers, so that the elements with similar properties fall in the same columns, okay? Groups, of course, are vertical, up and down, okay? And you have groups 1 through 18. And then it should say periods, not periodic. I don't know why it says periods. But periods, let's change that right now. So it's periods. Mark that out. And periods are the horizontal rows across, side to side. Okay? Periodicity is the similarities of the elements in the same group is explained by the arrangement of their electron configuration. Because remember, everything in the same group has the same outer electron configuration. For example, group 1 has an S1 configuration. Either it's 1s1, 2s1, 3s1 as you go down the group. So it's their electron configuration around the nucleus that gives them these similar properties. So let's talk about the S block, which is groups 1 and 2. So the S block, we're going to talk about group 1 first, which is the alkali metals. And the alkali metals have some very unique properties. They are soft, silvery metals, so soft that you can cut them with a knife. let's just go ahead and put them all on there, and then we'll talk about them. Okay? They're soft silvery metals, I said, that you can cut with a knife. You can cut with a knife. That's how soft they are. They are the most reactive metals of all of the metals. As a matter of fact, they're so reactive that they are never found free in nature. Never. They're always bound up in a compound. Now, we can isolate them, okay, but we cannot find them free in nature. They react with water to form an alkaline or basic solution. Matter of fact, they have to be stored. If you are able to isolate them, you have to store them either under kerosene or mineral oil. They also react with air, so that's another reason that you cannot find them free in nature. Okay, so whenever you mix lithium, sodium, any of the group 1 metals with water, it will explode and produce an alkaline solution. And there's a really cool video that I'm going to show y'all in class tomorrow about the alkali metals. Okay, so let's move on to the next group. Okay, and of course, since they are in since they're in group 1, they end in the NS1 configuration. So that means that they have 1 valence electron, right? 1 valence electron. Because remember, our valence electrons are our outermost s and p orbitals. And so all of the group 1 metals have 1 valence electron. That brings us to the alkaline earth metals, which is group 2. They are less reactive. They are also not found free in nature. And they're harder, denser, and stronger than the alkali metals. The NS2 configuration means that they have 2 valence electrons in their s sublevel. This makes them a little less reactive than the alkaline in group 1s, but they are still very, very active. That's your things like calcium, magnesium, and strontium. Those are just 3 of them. The D block elements, of course, is the transition metals, okay? They're harder and denser than the alkali or alkaline metals. They're less reactive than the group 1 and 2, and for the most part, their outermost electrons are in a D sublevel, okay? They have those exceptions to the electron configuration that we talked about last unit. And remember, oops, sorry, too far. Remember, they're filling the D orbitals, okay? And so they're going to have, anywhere from D1, D2. Now, this is the whole block from 3 to 12, unlike groups 1 and 2, who each had their own name. This is the whole block, okay? And these are very, very dense metals. These are the ones that are used in things like jewelry and, wiring, things like that, because they're harder and denser and less reactive. As a matter of fact, some of them are so unreactive that that's the ones we tend to use in jewelry, like gold, silver, platinum, palladium, those kind of things, because they don't react with many things. Exceptions to the electron configurations are found in this group. We've got copper, silver, and chromium. We also have molybdenum and gold that we had to learn. So those are some of those. Their irregular electron configuration means that we sometimes can't predict, okay? Sometimes it's the electrons move because, one, it will become greater stability, like we talked about in last unit. It's important, though, that we define stable, because some of you had trouble with that on the test. Stable means that either all the orbitals are full, half full, or totally empty. Okay, so those are some of the reasons why they do the things that they do. We already talked about this, so we can kind of skip over this. The configurations that are, actually, let's just say, I'm going to tell y'all right now, just kind of skip over this, because we have already talked about this, and we've already talked about the ones that we had to memorize. So your transition metals, looks like we left out a slide back there, so let's go back to that. The transition metals have your classic metallic properties. Okay, your classic metallic properties. And that is malleable, which means you can hammer it into sheets. They are ductile, which means you can pull it into a thin wire. They have luster, which is a fancy word for saying they are shiny. And of course, metals are very good conductors. and your transition metals have more of those, oops, that's spelled wrong, classic metallic properties of being able to pull it into a thin wire and that sort of thing. Okay? The p block, which is groups 13 through 18, okay? The p block means we're filling up the p elements, or the p orbital, excuse me. They contain both metals and nonmetals, okay? So if you look at your periodic table, I don't know if yours has the zigzag line. If not, we'll do that in class. But there's a zigzag line that starts with boron, and it goes down, and those are the ones that are, it's like the cross between the metals and the nonmetals. They have, the metalloids are actually the ones that touch the zigzag line. They have characteristics of both metals and nonmetals. Many are good conductors, but they're brittle, okay? The metalloids are boron, silicon, germanium, arsenic, antimony, and tellurium, okay? And those are the ones that we need to be know on the periodic table that are our metalloids. The thing about metalloids is they make really good conductors, or semiconductors actually, not good conductors. That's why they're used in electronics, because they'll conduct some electric current, but not so much that you fry your circuit board. So silicon, of course, you've heard of as being a really good semiconductor that's used a lot in electronics. Group 17 gets its own name within those p block elements because it's very important. They have 7 valence electrons, okay, because you're at an S2P5, remember? So they have 7 valence electrons. So they're very, very reactive. They're the most reactive of the non-metals, okay? They are called salt formers, okay? And that you need to add that to your notes, and that's because they react vigorously with metals to form salts, okay? And a salt is basically a metal and a non-metal bound together. A lot of times we think of salt, we just think of table salt, NaCl, which of course has a halogen in it and a metal. But a salt is a whole class of compounds. And if you could get that into your head right now, it'll make a unit that we get to later in the year a lot easier, that don't think just NaCl when you see the word salt in chemistry. It can mean a variety of chemicals, okay? Most are gases. The one, bromine is a liquid, and iodine is a solid, okay? The rest are liquids. They are things that we use them like in toothpaste, because we have fluorine in toothpaste, cleaning supplies, anything you want to sterilize, like bleach, is made of chlorine, of course your swimming pools, that sort of thing. Those are what they're used in a lot. They are, they like to react with group 1, because group 17 needs 1 electron to get to 8. Group 1 wants to get rid of its 1 electron so it can bump back down to 8, like we talked about in a previous unit. So they like to react together quite a bit. But they're also very reactive with group 2 as well. That brings us to group 18, which is the noble gases. And as we talked about last unit, the S and there's the S2P6 is what its outermost electron configuration is, which gives them 8 electrons, because now they have a full octet, and that makes them very, very stable. They are all odorless. They're all gases, but they're odorless and colorless also. Anytime you see neon, I know you're thinking neon gas is not colorless necessarily, but they put something in it, usually one of the metals, to make it have a color to it. They are very unreactive. They're unreactive because they are have that high stability of the octet. Together, when we talk about the S and P blocks together, we call them the main group or representative elements. And the reason they're called that is, honestly, they're the things that participate in the most reactions that we deal with, okay? After that would come the transition metals, because we do some reactions with those, but a lot of the transition metals are not very reactive, like gold and things like that. But they're the S&P blocks are your main group elements, okay? The F block, of course, that's the part at the bottom that is separated from the rest of the periodic table, and of course they're filling the F blocks. And remember, on your periodic table that has the lanthanide and actinide down there with the F block, but they don't belong there. They belong up there in the D1 slot. And so you need to, if you haven't already written that or drawn arrows, you need to so that you understand that. So the F block, the first one, is filling the 4F sublevel, and that is the lanthanide series. Okay? And they are shiny and reactive metals, relatively reactive. We don't do a lot with them. But they are filling the 4F sublevel. The actinide series are very unstable, and they are all radioactive, and they are filling the 5F sublevel. So that brings us lastly to hydrogen and helium. Okay, hydrogen and helium, they're the oddballs. They're up there all by themselves. Obviously, if we're looking at hydrogen, we know that hydrogen is not an alkali metal because it's a gas. Okay, if you're looking at my big periodic table on the wall, anything in red is a gas, and anything in blue is a liquid. So there's only two liquids, which are bromine and mercury, and then the rest are solids. Okay, and then the ones that are outlined are the man-made ones that we don't know much about, and they don't exist for very long. But anyway, so let's get back to hydrogen and helium. Hydrogen is not an alkali metal. It is a very reactive gas, and it is placed with the alkali metals just because of its 1s1 configuration. Okay, but it has many unique properties, including it's the only element that doesn't have a neutron. Most of the isotopes don't have a neutron. It's also the only element when it gives away its electron, which it likes to do, it will have no electrons as well. Okay, and so when it forms an ion, so if it gives away its hydrogen normally has 1 proton, 1 electron, and 0 neutrons. And so when it gives away its electron, it becomes a H+, so basically it only has 1 proton. And so a lot of times if we refer to a proton, we'll call it a hydrogen ion as well, because it's kind of the same thing, because that's the only thing that's left in it. Helium is a noble gas, okay, but it is unreactive. It does not have 8 electrons in its outer most configuration. So you need to make note of that, because a lot of times people will tell me that it's got 8 electrons because they look up there and go, oh, it's group 18, 8 electrons, it's got S2, P6, okay? So it only has 2 electrons, okay? So please make note of that, because later on when we get to electron dot notation, people will draw 8 electrons around helium, and it is incorrect. So helium is 1s2. It's up there by itself because they're strange. And that is where we are going to stop today. And remember, if you need to rewatch the notes so that you can make sure you got a handle on it, because you will be taking a quiz. The next unit will be the trends.